for this lecture. And then 5 out of 6 times I found myself still on the conference call when I teach. This reminds me of something that very important. Some of you would begin to give conference calls, not conference calls, conference presentations, and then you'll be wearing these microphones. So after the presentation, if you go to the restroom, be careful about what you say about other people's presentations. This is a real story. Everyone was hearing about this person bad-mouthing other people's presentations about the restrooms. Be careful. Okay, how are we doing so far? The MPs okay? Okay, keep making progress. Okay, they keep coming. They come slowly, but they keep coming. So make sure that you really understand. And so we're going to be releasing another quiz in the next couple of days as well. So just kind of pace yourself. Okay, keep making progress. Some of you are reading, doing some extra reading. Keep doing extra reading, and if you want to get some more reading, especially in the hardware background, we can connect you guys so that you can have more of the discussion, because this is also a good opportunity for you to understand the hardware more deeply, right? So that you can have even more skill as you go through it. So last 2 lectures we talked about breadth first search, and it's really meant to be a very quick introduction to graph, right? To graph and how in reality we represent graph in high performance computing and GPU computing. And we really don't use breadth first search for most of the graph analytics. The breadth first search is essentially a way for you to find the shortest smallest number of hops that you need to take to go somewhere. Probably the most common algorithm is actually shortest path, right? And so for GPS, for example. On the other hand, there are many very high valued what we normally call the graph analytics that give us from some kind of very large amount of log information for us to be able to figure out some of the behavior. So I'm going to use triangle counting today to give you a little bit of introduction into these kind of analytics, and then we're going to talk about how you can do a little bit more work to be able to get information that is the kind of a higher level information about the graph. And then next time we're going to go into trust decomposition that uses triangle counting to be able to give you even higher level information. So the idea of these things is that you have a vast amount of information, and then you try to to get a little bit of the structured information, and hopefully a lot smaller amount of information from that. And then you use that to build up even another analysis to get even smaller amount of information, but even more meaningful information, right? So the objective is for you to become familiar with the parallel graph analytics algorithms. For triangle counting, we're going to look at triangle counting for undirected graphs. And these graphs, really the edge of graph is describe some kind of relationship, okay, between these nodes. And we're going to see, we'll talk about a few examples. And then this is actually a very important foundation for community detection. And community doesn't have to be people. Community could be products, okay. Community could be even the geographic locations and so on, right? So these community just means that there are a subset of the nodes that are closely related to each other, and you can when you do something with one, you want to think about others. So these graphs usually they describe connections, temporal relations, causal relations. So for example, an edge may actually mean that you and I have a Facebook connection, right? We're connected, right, in the Facebook or LinkedIn kind of thing, right? So those are straightforward. You could have some kind of temporal relations. For example, each edge may represent two products that in a typical Amazon, Amazon user browsing session, they are viewed together, right? You view one, you view another, you view another. So then you put edge between these products, so that sometimes you may have directed graphs, meaning that you may say, after I view this product, the user views this product, the user goes to the next product. So then you represent even more sequencing information. But you could just have a n-directional edge saying, well, whenever there's an edge, that means that in one of the sessions that user browse, they would view these two products in that same session, right? So you can have also causal relations, relations. So that would be typically directional graph. So if you have done this, you would do something else. For example, if you purchase this product, you will purchase another product as a result. Okay, so typically when you buy a cell phone, you will buy screen protector or something, right? So there's some usually that you can represent. You may not know exactly what they are, but you notice that whenever immediately after someone purchases something, they always go and purchase something else, right? So these are the kind of things that Amazon makes billions of dollars with. Okay, and we typically say that Google made billions of dollars by figuring out the page ranks, right? Then Amazon made billions of dollars by figuring out what people buy together, or what people buy, after they buy something. So it's kind of a simple, very simplified description of how the technology is used to make money. So we can mine these graphs, to get high-level information. For example, which community does an individual X belong to? So if let's say if you look at Facebook, right? There are a lot of these groups, right? A lot of these things, but sometimes these things may be informal. That is, they may not have formed a explicit group. But if you look at the connections and so on, sometimes you can discover that they're informal groups. So the explicit groups are what we call the structured data. That is, the groups actually mark, right? You mark all these nodes. So those are metadata-based structured information. But informal groups that evolve over time and so on can actually be very, very valuable for people to target, advertisement or things like that. So these are unstructured information that you need to discover, right, from the general graphs. So who are the leaders of the community X? If you look at a typical situation, you may see a few individuals that are connected to everyone. Okay, and these are the rumor mill sources. Okay, so whenever this person does something, everyone else will know. So those are the kind of the community leaders. Which are other products did individuals end up buying after they viewed product X, right? So as soon as you end landing one of the product page of the Amazon, it will tell you those people who have viewed this product also viewed, right? And in fact, sometimes they even say those people who when people view this product, they ended up buying something else, right? So usually that means that people already spend time looking for a better deal, right? So whenever you view this product, chances are someone already found a better deal. And these are the ways for Amazon as an independent, carrier to provide value, right? To provide value to the shoppers, right? So those are the kind of things that Amazon would try to do. And it doesn't really cost them anything, right? On the other hand, people feel that when they come to this site, they can more easily find better deals, right, than other sites, right? So that's the point of some of these analytics. Which freeway sections are bottlenecks in this particular area? You probably have seen this phenomena that you know, when you have, you know, let's say a freeway system in Chicago, you know, there's a section in 1994 that is close to 290 and 55. That's the bottleneck. And, you know, so, you know, of course, if you drive on these freeways, you know, right? On the other hand, you know, if you have some kind of planning, right, and then you say, okay, I'm going to plan my freeway this way, and then I have some kind of, you know, projected or expected traffic patterns, can I analyze it and say, oh, this is going to be the bottleneck in the future. I need to build it differently, right? And these people didn't do that. That's why that section exists. Okay, and I think you guys probably know what I'm talking about. You know, from 57, you know, a little bit after 57, all the way to a little bit north of 290. Okay, that section is terrible. Okay, so you know, whoever built that freeway did not have the graph analytics technology that we currently have today. Anyway, so those are the kind of things that you know, graph analytics can do. And it turns out that many people you know, understand you know, these kind of things. You know, for example, you know, when we talk about you know, committee assignments, and when we talk about resource usage and so on, you know, there's a very long history of literature, you know, that formulate these things as graphs, and then formulate the, you know, the assignment problem, the resource usage problem, the planning problem, and so on as graph analytics problems. So let's, you know, talk about something, you know, simple. Triangle counting is perhaps one of the simplest form of, you know, graph analytics. And so it finds the number of triangles in a graph. And why is it interesting? You know, if you think about it, graphs are nodes and edges. The relationship between any two nodes are already represented explicitly in the edges, right? So, you know, triangle counting finds the relationship among three, right? You already have the relationship between any two. You have an edge, you don't have an edge, but what weight the edge carries. So the next level of information that is not explicitly represented in the graph will be relationship among three, right? So you can ask, you know, what are the three entities that have, you know, essentially a fully connected situation, right? You have, you know, when you have these three nodes, and there are three possible edges. And if all the three possible edges exist, then you have a triangle. That also means that every pair of the nodes in that, you know, in that triangle have a relationship. So it's a full, it's a full relationship. It's equivalent to the edge, right? So that's why it's interesting. So it's a foundational function for community analysis. When you have a graph, and you say, I have many triangles, that means that, you know, the community is heavily connected. It's not just, you know, the pairwise connection. You know, you have a lot of these three-way, you know, connections. So that means that there's quite a bit of connection, you know, in that community. So the community has strong ties. Whereas, you know, if you have very small number of triangles, that means that you know, these things are mostly just pairwise connections. So there's not a whole lot of these, you know, more than two people kind of, you know, circles or you know, communities in that community. And this actually can, you know, you can use this in a kind of recursive way to determine you know, big communities and, you know, identify bigger communities with these kind of, you know, basic building blocks. So there are multiple ways you can do triangle counting, just like there are multiple ways you can do breadth first search. Remember, we talked about algebraic, right, method. You can do matrix vector multiplication to do the you know, the frontier propagation, right? So here, same way, we can use linear algebra, and we can, you know, compute triangles through matrix operations. Remember, Professor Del Padua is right. Matrix multiplication is very important. Okay, because there's so many things that can be formulated with matrix multiplication. And so you can also do neighbor intersection, and you can count the size of intersection of edge neighbor list. And by the way, these two are isomorphic. You can actually prove that they're totally equivalent to each other, and that also will tell you how you can optimize between the two. So. And then subgraph matching, you can enumerate subgraphs that are isomorphic with the triangle graph, and but that's way too abstract. And so, but if you're interested, you can do something. It's a little bit too abstract for my taste. But if you're theoretical, interested and so on, feel free to to do some of that and come back and talk to me about the convince me that it's of some practical value. Okay? So many years ago, I decided that I'm an engineer. I'm not a scientist. What that means is that I'm interested in things that I can build, things I can I can kind of play with and so on. And when it gets a little bit too abstract, I say, well, that's interesting, but someone else can do that for a living. Okay? I do this for a living. Okay. So you guys can figure out what you want to be. And it's perfectly fine to be a scientist. It just as long as you know how to make money, make a living out of it. Okay, it's great. Okay, so one of the things that that we typically do for analyzing these any undirected graphs is to try to improve the efficiency of our analysis. For example. Let's say if we start with an unidirectional graph, right? So remember those products that get that are viewed together or purchased together in the same session, right? Those are undirected graphs. So if we have an undirected graph, and we want to count the triangles, we may end up with being able to, let's say that if we decided to do triangle counting by taking one edge, right, taking every edge, and then count whether this node and this node have a common neighbor. Because we don't know where the triangles are. So we will probably start with all the three edges, right? We'll start with all the three edges. And for each edge, we're going to see if the two nodes of that edge have common the common neighbor node. So we will most likely end up with three triangles out of this. We take this guy, we found this triangle. We take this guy, we found this triangle. We take this guy, we found this triangle. In the end, we divide by 3 and we get a number, right? But that's a kind of an awfully wasteful way of counting, because we're counting everything 3 times and then divide by 3. So it would be nice to not to have to go through that redundant counting process. So that's why whenever possible, we would like to convert unidirectional graphs into directional graphs and impose a couple of rules to make sure that we only count do the counting once for each triangle we're going to find, right? So that's so that's why. For example, if we only generate the direct arc such that the source is always less than destination. Okay? So we say we have an unidirectional graph, but all the nodes are numbered, right? Doesn't matter how you number them, but once you number them, there are small numbers and bigger numbers, right? So we say, okay, when I convert from a unidirectional graph to a directional graph, I'm only going to have draw an arc if the source is greater than is less than the destination. So in this case, 1 is less than 4, good, right? 1 arc here. 2 is less than 4, 1 arc here. 1 is less than 2, an arc here. So we end up with 3 arcs, but the direction, right? Each one is a directed arc. So now, if I start to, if I represented this graph as a directional graph, remember, when I take this arc, these are 1 and 4, right? So 1 is still going to have a node, an arc out, but 4 is not going to have an arc coming out of this, right? So I'm not going to be able to, I'm not going to see an arc coming out of 4 that will give me that intersection. So I'm not going to go down this path. Same thing here. If I have 2 to, look at 2 to 4, 2 to 4, neither one has an outgoing edge, right? So I'm not going to, to try to do that intersection with this one either. The good thing is 1 to 2 both have an outgoing edge, and then we're going to see that intersection. So the intersection only going to happen once, right? When we have this total ordering, and this allows us to, to go through these tests and the finding. We're only going to find exactly the number of triangles rather than finding the triangle 3 times and then divide by 3. So if we impose the right kind of ordering and generate a directed version of the undirected graph, we can actually control the amount of computation, lower the computational complexity. Actually, it's not lower the complexity because it's just a constant number, right? But we can be more efficient, right? Yes.
Do you care how to assign like a number to each node?
No. So it's whatever you decide to assign, then you follow this rule. Yeah. So that's the main thing. So basically, once we determine a rule like this, there are actually multiple kinds of rules you can follow. But once you determine a rule like this, you will have a unique representation when converting from undirected graph to directed graph. And only one triangle will be detected if we use neighbor intersection, right? So this is what I just talked about, right? So this is good. So let's start with something like this. This is, let's say this is a graph of 5 products, and then this describes, for the different, for different user sessions, this product tend to be brought together, these two tend to be brought together, and so on, right? So you have a graph like this. It's undirected. So if I need to detect a triangle, I convert it into a directed graph. And so we also make sure that it's acyclic. By only going in one direction, that is, you can only go from small to big, you will not have a cyclic graph because you cannot come back to a smaller node, right? So that's another good thing. You can actually prevent cycles in your graph. And by the way, none of these things is particularly parallel. Right? I'm probably just reviewing some of the things for you, from something like 374, right? So it may not emphasize it from some of these angles, but it should have pretty much covered most of this. So once I have a directed acyclic representation, this is a conceptual representation. Remember, we can have that adjacency matrix, right? So I have source, I have destination, and so whenever I have a arc or an edge from a source node to a destination node, I would put a 1 to it. So this is from node 0 to node 1, right? So from node 0 to node 1, I have an edge, so I have a 1 here. And by now you should have also noticed, if I impose a rule that source has to be less than destination, I will end up with a triangle matrix, right? And it's actually a sparse triangle matrix. And if I impose the other direction, that the source has to be greater than destination, I will end up with a lower triangle matrix, right? So these things actually change the shape of your physical storage, how you end up storing the data in your memory. So adjacency matrix review, all good. So one thing that we will use quite a bit is the node degree. So some of these nodes have a lot of outgoing nodes. That means that product is frequently purchased by with other products, right? So that probably means that it's a very generic product that can be used along with many other things. So in this case, what one has 3 outgoing arcs. So the degree is actually outgoing degree. Okay, outgoing degree. So the one has 3, and 2, you only have 1 coming out. So that's 2 to 4. So that's 1, and 4 doesn't have anything going. So 4 will be 0. Right? And, which makes intuitive sense because 4 is the largest node. How can it go anywhere, right? So it should be 0. So, so that also kind of goes into one of these random things. Okay, this is what I call the one-make-who random things. So I'm going to write a book called One-Make-who Random Things eventually. So what I just talked about is when you have a totally ordered graph, and the largest node should have no exit, no outgoing arc. These are the properties that you can use to check, to do sanity check, and then to know that something went wrong, right? And it's very, very important for engineers to always keep track of all the invariants, all these properties, so that when something goes wrong, you can immediately tell. You don't have to you don't have to run a program to tell something went wrong, right? And that's actually really, really important. I still remember, there was a student, and when I was in high school, we were using calculators to calculate these the trigonometry functions, and then one of my classmates putting a whole lot of numbers. It was a pretty complex calculation, and then eventually came up with 1.7. And so I said, this cannot be true. And they said, why? I said, you're adding 2. Eventually this thing has to be less than a sign value of some sort. And then how can that be greater than 1? Right? So when you write anything, code and think, don't just write code. Think about what you're really doing, okay? And then think about all the properties that these things should happen. This is the reason why we teach these proofs, right? The proofs are really there to help you to establish some of this intuition and understanding of the properties. Okay. So total node ordering, I just talked about this. Source is less than destination, right? You can have source greater than destination, so you can have either lower or upper. We're going to we can have either ways. In some machines, apparently lower triangular matrices are more efficient to access than upper triangular matrices and vice versa. And it's kind of interesting. So you could just pick these things based on your performance, performance preferences and so on. Or you can actually do something like this. You can order them through node degree, and of course for node degree you're going to have ties, right? So then you can just use the let's say use the node ID whenever there's a tie to break the ties. So what's good about this? Because if you just make sure that you always use put an arc if the source degree of the source is greater than the degree of the destination. Remember the arcs. Okay, the arcs goes from source to destination. So if I always use this way, then the degree of the source is going to be the degree of the source is going to be a lot of high essentially whenever you have a large sort of a neighbor node, you're going to be making it actually it should be probably less than. So because we're going to see, okay, this guy has a large number of neighbors, we always get to make it the source. So then that means that these things will tend to have a large number of outgoing arcs. So if you do a smaller NAND, then you will have, most of the nodes will have minimum number of outgoing arcs. So this may actually give you, better potential load balance because you tend not to have ridiculously high number of outgoing arcs in your graph. You kind of regulate it a little bit like this. And so I think this is probably smaller than that. So, but whenever you want to do this with no degree, you need to have the entire graph in place to be able to do the conversion. Why? Because if you add another few nodes, suddenly the node degree can change. Right? So if you just add a few nodes, you may need to redo or update, right, extensively the ordering. So you need to change the numbers. You may need to change the numbers quite dramatically. If you just add a small number of nodes into this. Whereas if you just use node ID, the later nodes can just use bigger numbers or something, and then it becomes a lot easier to update. Okay, so let's start with how we can do triangle counting with linear algebra. Okay, so how we can do triangle counting by manipulating matrices. Okay, so here is a simple graph. So I'm using the rule that the source has to be greater than the destination, right? So 3, 1, 3, 2, 2, 1, 2, 0, and 1, 0. And this gives us a lower triangular adjacency matrix. Node 1 will be able to go to node 0, right? And then node 2 will be able to go to node 0 and node 1, right? So it's a lower triangular adjacency matrix. So whenever there's an edge that exists from node I to node j, then this L link matrix will have ij to be 1, right? So if I do a matrix multiplication and then do a element-wise element multiplication, I will get the number of triangles. So, that's interesting. So let's talk about the intuition here. The intuition is this. If I look at the row, okay, matrix multiplication is a row of this matrix and a column of this matrix dot product together, right? You do a dot product between the row and the column, and then you generate an output element. So let's say the output element, ij. So I will take the ith row, okay, I'll take the ith row of the first matrix. These are identical, by the way. These both are the same adjacency matrix. So basically, this row is telling me all the destination nodes that this particular source can go to, right? All the destinations that the source node can go to. This column shows me for a destination all the sources that can come in. Make sense? So basically, I'm saying, starting from I, all the nodes that I can go to, right? And then ending with j, all the nodes that can come in. If I do a product, dot product, and say I can go from node I to 0, and the other one says I can come from 0 to j. That means I have a path. I have a little bit of a wedge path from I to j, going through 0. So when I do that dot product, I'm going to have 0, 1, 2, all the possible intermediate nodes, right? All the possible intermediate nodes. And if I do the product, I'm adding up all the ones, right? I'm adding up all the ones. Remember, these are all just 1 and 0s, right? So I'm adding up all the ones in that inner product term. That gives me all the possible one hot paths I can have from node I to node j, right? So what is a triangle? The triangle is you go to somewhere else, come back, and then you also have a direct path there, right? That's a triangle. So now I have found the number of these wedged, right, indirect path, right? If I multiply that with the number, with the original adjacency matrix, that tells me, each one tells me there's a direct path from I to j. So the first one tells me that there's an indirect path going from another node from I to j. The second one tells me I have a direct path from I to j. If I multiply them together, that whenever there's a non-zero entry that tells me the number of triangles I have that goes between I and j. Okay, the edge of I and j is involving all these triangles, because the number of triangles is all these number of indirect paths that I can find in the graph. Any questions? Let's do one example. Okay, let's do a concrete example here. Let's say if I want to do here, node 3 and 0. Okay. So do I have, how many triangles do I have between node 3 and node 0? If I look at the original graph, 3 eventually will go to 0, right? It goes to 1. Or it could go to 2, right? But is there any triangle involved? Because there's no direct path from 3 to 0, right? So there's no triangle, right? So if I do this multiplication, I do a dot product of row 3 and column 0 of the adjacency matrix, I actually have these two ones here, right? This means that 3 could go to 1, and then this means that 0 can come from 1. Here, 3 can go to 2, right? And this means 0 can come from 2. So the fact that we have 1 in both these locations and these locations tells us that there is an indirect path. There are two indirect paths. I can go from 3 to 0. One goes to 1, one goes to 2. Right? And indeed, if you look at the graph, you can do this or this. So that's the matrix multiplication. So once I finish the matrix multiplication, I say there are two indirect paths, right, that can go from 3 to 0, right? Row 3, column 0, going from 2 to 0. So those are the number of wedges that I can have. Any questions? Yes?
So why don't you like the sparse matrix format? Because I mean there are a lot more zeros than ones.
Yeah. So if it is a truly, I'll come back to that. So this formulation works well when you have a dense matrix. If you have a truly a sparse matrix, you're going to be doing a whole lot of wasted computation because of this, right? Because you're going to be doing a lot of zero, the multiplications, right? Exactly right. So here, if you have here, so if I ask the same question about 0, so remember this thing is 0 here. So when I do a pairwise multiplication, that tells me that there's no direct path from 3 to 0, and there are two indirect paths, so they don't form a big triangle. So that's why the pairwise tells me that there's no triangle here. Okay. If I move just a little bit, I said, okay, how about from element 3 from node 3 to node 1, right? So when I do the multiplication, I will have, if I go back to the multiplication here, if I take 3 and 1 here, right? So I'm going to have this guy. This is the common guy, right? So I'm going to end up with 1 in 3 and 1, column 1. So this tells me that there is a path, indirect, only one indirect path from 3 to 1, right? So which is, right? This is the indirect path. And there is also a direct path from 3 to 1, which is this one, right? And now it forms a triangle. Does that make sense? Okay, good. So you can do the same thing with others, and you know, so make sure that you know it becomes essentially you know second nature for you. So in general, if we literally do a matrix multiplication, we're going to actually generate a fairly large product matrix. And most of the elements will be likely be 0 because there are not too many triangles, right? In a especially in a sparse graph. So we're going to be matrix multiplication is an n-square algorithm, right? So we're going to be generating a very large number of the elements, and then we're going to access that very large number of elements through the through the pairwise multiplication. So this whole thing will be likely be very, very slow. However, if you really want to, find all the triangles quickly, that is, you want to be able to have a data structure that gives you all the triangles, then involved with every edge, then that matrix is actually going to be really, really helpful. So you can quickly flatten the matrix or reduce the matrix in some way to get all the numbers that you want, any kind of analysis. Okay. So this is kind of the the interesting cost and benefit for this matrix formulation. So in general, when people do this calculation, they don't explicitly represent all the product matrix elements. Right? They would generate it on the fly, but then they would immediately multiply with the, multiply with the original adjacency matrix, and then just generate the final matrix. So this is a very, very common technique that many people use when the matrix are very big, but you have some rules for consuming them, for the rules for generating them. Oftentimes they don't represent the matrix in the memory. They either use the rules to generate the elements on the fly, or they generate the matrix but consume it right away rather than writing it to the memory and then read it back. Right. So this is called streaming, right? So it's a very common technique that people use. So that's algebraic representation. As you, what's your name? Suna. Suna correctly pointed out, whenever you have a very sparse matrix, this is a bad idea. Okay. On the other hand, you may have regions. You may have regions that have very dense distribution. Okay. So whenever you have these pockets of very dense representation, you can potentially use the matrix formulation for that dense region, and then you use a different method for all the remaining edges. Right? You can take out those edges once you do the dense counting, and then you can use the remaining edges, in these other representations. So people use this kind of hybrid, technique quite a bit, in whether it's in the linear solvers for for linear algebra, or matrix decomposition, or in some of these kind of triangle counting kind of things. So that's algebraic method. The other method that that is very, very common is the triangle is the set intersection method. So basically, we say for all the edges, we derive the intersection of the neighbor list of the source and destination. Okay? So if we have let's say an edge here, maybe this particular edge from 2 to 3. Then we find the neighbor list, which is 2, we have 1 coming out of 2, so that's 2 to 4, and we have the 1 come out of 3 to 4. So each one has a neighbor edge, right? An edge coming out. So we take the intersection of these two and say, these two both have the same destination. So this is the intersection. That means that I have an edge here, and then both have an edge to the same node. I have a triangle. Okay, so that's the intersection method. So the way that we, for this is, you start with edge 2, and then you say, okay, the neighbor of 2 is, that is 3, and 2 is 3 and 4. So this is the set, and the neighbor for 3 is only 4, coming this way. So when I take the intersection, I only have 4 here, and that's, that gives you 1 triangle. Okay, so this, is the intersection method. So when you do the intersections, you can have various different ways of doing the intersection. Depends on whether your neighbor list is sorted or not sorted. If you have pre-processed your graph so that all the neighbor lists for the node, for the nodes, all the outgoing edges for the nodes are going into sorted order destinations, then you have a simple way of doing this. Essentially, it's a merge pattern, and we're going to talk about the merge pattern later this afternoon, this semester. But I'm going to show you just the kind of how you can do this for this particular computation. Basically, if both lists are sorted, then you can just go through both lists and then see which list is still behind the other one, and you don't have to do all the random random stuff. You can just scan through both lists once, and then you're done. Okay, you can find all the intersections. And but if it's not sorted, then you will need to do a lot more work, and then you need to essentially the outgoing degree times the outgoing degree of the two nodes. You will need to do the work that is the product of the outgoing degrees for both nodes. If you don't have sorted method, sometimes you can do hash method. That is, let's say I have a destination node from one of the source, and I want to see if this node is in the destination node list of the destination, right? So if I have a hash table that that map all the destinations of the destination node in a hash table, then I take the source. I can just have an order 1 access into the hash table, right? So this is a typical way of searching at constant complexity. But the problem is you need to build a hash table. So you either sort it or you build a hash table. You're paying cost for the preparation, and then hopefully you can do things very fast. Then you can do binary search. That is, if both lists are, if at least one of the lists is sorted, you can actually take let's say, if one of the lists is sorted, you have another list. You just take these other elements, and then for each element, you do a binary search in the other list, and then you can quickly find whether it's matched or no match. So the trade-off is this. The trade-off is that if you do something like this binary search, okay, if you do this as a binary search, you can parallelize all you want, because you can take all the elements of that first list. Every element can be done with a thread, right? And then every thread is going to just